Well, apparently p-value is a very important concept in statistical tests, and many people have some difficulties in understanding the p-value. But in fact, it's not the only outcome of statistical tests. There are actually some more, and that's what we are going to discuss in this part of the lecture. Well, let's talk about errors in hypothesis testing. So when you make a test, you have to make a decision, right? So you either reject null hypothesis or accept null hypothesis. So what this decision may lead to, may you have a wrong decision, actually, in this case. Actually, there are two types of errors in hypothesis testing. The type 1 error, you already know it. It's incorrect rejection of null hypothesis. It means that you reject null hypothesis, but it's a wrong decision, okay? Well, and the only thing that this type of error depends on, it's your significance level. It's how small p-value should be to reject your null hypothesis, right? So for you have to compare it with something anyway. So if you compare it with 0.05, then that's the chance that you will make a wrong decision. If you compare it with 0.01, that's the chance that you will make a wrong decision. If your p-value, for example, is 0.01, there is still 1% chance that your sample came from the population where null hypothesis is correct. So if you reject null hypothesis at p-value 0.01, 1% chance that you will make a wrong decision. And that's actually a type 1 error. But there is one more. It's a type 2 error, when you cannot reject it because p-value is relatively large, but in fact it's wrong. You never know, is your null hypothesis correct or wrong? Of course, in most of the cases, because we take null hypothesis as something most expected or more natural, type 2 will not be that important, but there are many cases where type 2 is also quite important. So let's discuss that. Well, first of all, usually these probabilities to have type 1 and type 2 errors, they are denoted by Greek letters alpha and beta. You remember alpha, we also used it for significance level, and that's actually the significance level gives you this probability. So alpha is significance level or probability for type 1 error if you use significance level to reject or accept null hypothesis. And then beta is the probability for type 2 error, when you cannot reject null hypothesis, but actually the null hypothesis is not correct. I will show you some funny picture, which you can find on the internet, that gives you an idea about the type 1 and type 2 errors, okay? So in this case, our null hypothesis is that person is not pregnant. Well, that's natural, right? So most of the time, people are not pregnant, especially males. But if, for example, in this case, we say you are pregnant, so it means that we reject null hypothesis. But this is a wrong decision because the person is not pregnant, right? This is type 1 error. So when you reject null hypothesis, but it leads to a wrong decision, it's type 1 error. In the second case, the person is apparently pregnant, but we cannot reject null hypothesis. So we say you are pregnant. This is a type 2 error. So when we cannot reject null hypothesis, but null hypothesis is not correct, then it's a type 2 error. Okay. Now let's discuss it with a little bit more real-life examples. You remember the river data, okay? So let's assume that we continue working with this river data, and that's our null hypothesis, okay? So the red curve, it's density distribution for possible sample values if the whole river has chloride content 146 milligrams per liter or less. So in this case, you can, for example, if the sample size is 10, and I use standard deviation for the sample is also 10 in this case. So that's all possible values. For example, you take a sample and the average of this sample can be 140. Or you take another sample and it will be 150. Or you take another sample, it will be 138. You take another sample, it will be 140, 154. So these are all possible mean values for your samples if null hypothesis is true. Okay. And you remember in this case, we use right tail to estimate the p-value, to estimate the extremeness of our sample, because we believe that the chloride content in the whole river is at least not larger than 146. So it means that if your sample has quite large average chloride content, then it becomes more and more extreme. Okay. Then if we use some rejection levels, for example, we say we would like to reject all p-values below 0.05, right? So it means that all these samples, the samples that are located here in this area, will have p-values less than 0.05. And you have 5% chance to get a sample like this. Okay, So if you reject all p-values, all samples with p-values less than 0.05, it means that you have 5% chance to make a wrong decision, because you still have a possibility, a probability that this sample came from this population. Okay. So the significance level gives you a probability to make a wrong rejection of null hypothesis, assuming that null hypothesis is true. So in this case, we assume that the sample is indeed from this red the population that is described by this density curve. Okay, so that's type 1 error, and we more or less know how it works now. What is type 2 error? Well, that's another thing. We still assume that our river is not contaminated. We assume that in the whole river, the average chloride content does not exceed 146 milligrams. But, and we don't know it, the reality is the blue curve. So in reality, the river has average chloride content 150. So it's by 4 milligrams per liter larger than the contamination level. Will we be able to see that? Well, look, our sample comes from the blue population, right? So every time we take a sample, it can be here, it can be here, it can be here, it can be here, all these possibilities, right? But we don't know that actually our river is contaminated. We believe that our sample is this one. Okay, how often we will not be able to reject null hypothesis? So all the time where we have the sample here, right? If our sample is here, we will not be able to reject null hypothesis, and it's actually 71% of the time. So the probability that we will not see contamination, even though the river is contaminated, but we will not be able to see it because our null hypothesis assumes that there is no effect, there is no contamination, is 71%. And that's pretty large, isn't it? Let's discuss this a little bit with a little bit more details. And first of all, let's talk about what parameters influence type 2 error. Okay, so what type 2 error depends on. So if we look at this one, think how we can decrease this blue area. So blue area, it gives us type 2 error. How we can decrease it? Well, apparently, first of all, the larger the population is from our null hypothesis, the bigger size effect, the bigger difference between the average of the population and average that we assume population has, then the smaller blue area will be, right? So if we have these two peaks more distanced, for example, if the blue peak goes in this direction, so it means that the distance will be larger, but the other parameters are fixed. The sample size is fixed, the standard deviation is fixed, so the shape of the distribution will be the same. And then if it goes in this direction, so it means that the blue area will become small. Okay, so the first parameters that influence the type 2 error is the size of effect. How big the difference is between your null hypothesis and the reality. The second is, of course, sample size, because sample size influences the size of the confidence interval. In our case, confidence interval is pretty large, right? You have, for example, for our null hypothesis, is somewhere the sample average can be between 134 and 158. It's pretty big uncertainty. And of course, if you change sample size, if you take a larger sample, this uncertainty will be smaller. So the width of both curves will be also smaller, and therefore the area of the blue area and type 2 error will be small. Okay, so sample size also influences type 2 error. And then the significance level. Think, if you change the significance level, if you change, for example, this rejection limit for 5%, if you change it, for example, for 10%, so of course the new blue area will be here. But the problem is, in this case, if your null hypothesis is correct, the chance that you will reject it, so the chance for type 1 error will increase. Okay, so when you change the significance level, you decrease one type and increase another type of the errors. Let me illustrate this using several examples. So in this case, we have original distribution. So we have our null hypothesis is that average chloride content does not exceed 146, and the reality is that we have 150, right? 150. What will be the size of effect? The size of effect is 4, right? It's just 150 minus 146. So that's the size of effect. Okay, so it's the difference between the true population average and our null hypothesis. Now, what if we change this? Or what if, let's say, the river becomes more contaminated? Will it change the type 2 error? Well, apparently yes. In this case, you see the new contamination average chloride content is 156. So the size of effect is 10 now because it's 156 minus 146. And now look at this. Now the probability for type 2 error is only 11%. Okay, so if size of effect is larger, then the probability for type 2 error gets smaller. Okay, and we fix the other parameters. We fix the significance level, we fix the sample size, and of course standard deviation of the sample is also this. So that's how size of effect influencing. Of course, it's not for this particular case. There is a hope that if river gets more and more contaminated, we will be able to detect it. But the small contamination, we will not. Okay. But actually, we can do something else. So the second parameter, very important parameter, it's influence of the sample size. So in this case, again, we have sample size 10. What happens if we take not 10 glasses of water, but 50? Okay, so that's the new sample size. Look, again, standard deviation is the same. Significance level is the same. The population mean and size of effect is the same. We just took the bigger sample. We just went and took more glasses of water from this river. Now, the spread, the confidence interval, is much smaller. The uncertainty is smaller. And therefore, the beta, the type 2 error, the probability for 2 error, only 13%. Of course, we will have to spend more time and more resources to analyze our samples, but that's the good price to pay, right? And then the significance level. Of course, if you cannot change the sample size, if you cannot change, of course, the size of the effect, you can always change the significance level. Okay, so once again, the default significance level I used was 0.05, and I took 0.1. So now what happened? Look, the red area becomes larger. So it means that the probability that we will incorrect reject our null hypothesis. So it means that river is not contaminated, but we will say seems like it's contaminated. It's getting larger. Now it's 10%. But the probability is that not to see the effect, not to detect the contamination level, this one, contamination level, is decreased by 20% almost. Okay. So changing alpha also changed the type 2 error. But of course, in this case, you also change the type 1 error. You increase the type 1 error.